Okay, so thank you, Anne-Laure, and thank you for all the organizers for this invitation. So this talk will be more on the nonlinear aspect of the workshop rather than the stochastic. And the aim of this talk is to show more or less how to describe internal waves inside an ocean, and so several tools that you can use to describe these waves. And so the outline will be the following. First, I will recall some basic facts about the case where you just have one wave, which are surface waves or water waves. And then I will describe what you can do when you have two fluids. So it's an interface between two fluids. And in the last part of the talk, which will be the main one, what happens when you don't have two fluids, when you have a continuous stratification in the density of the water in the ocean, and how you describe propagation of waves in this framework. So as I said, I will start with the simplest case where you just have one fluid, which means that actually you have two fluids, but you neglect the density of the air, and you want to describe the evolution of the surface of the water, which is parameterized by a function zeta, and then you have a bottom, which I will take flat to simplify in the next slide. So the equations I will consider are the Euler equations, So in the fluid domain, you have Euler equation, dtu plus u grad u is equal to pressure forces and gravity forces, incompressibility, and also irrotationality, which is standard for water waves propagation. Okay, so these are the equations in the fluid domain, which are classic equations, and then you just need to complete them. You need some boundary conditions. So there is one at the surface, which is that the pressure at the surface is given by the atmospheric pressure, which we can assume to be constant, for instance, and you might have some surface tension terms. So I will comment on this surface tension coefficient later, which is essentially irrelevant for the propagation of surface waves, but which is necessary for the propagation of waves at between two, when you have two fluids at the interface of two fluids. Okay? And you need the second boundary condition, which is a kinematic boundary condition, which states that fluid particles don't cross the surface. So it's quite easy to check that this relates the time derivative of the surface parametrization to the normal component of the velocity at the surface. So u bar is the velocity evaluated at the surface. Okay, so these are two boundary conditions at the surface. And you need one last one at the bottom, which is that the bottom is impermeable, so the velocity is tangential at the bottom. Okay, so these are the standard water waves equation, Euler equation, boundary condition at the surface, and boundary condition at the bottom. So how do these equations work? So very simply, what are the main parameters and quantities in this equation? So it's quite easy maybe to see it if we introduce this quantity, which is u bar will be the velocity at the free surface. So v is the horizontal velocity, w the vertical velocity. And then what you can do is that you can take the trace of Euler equation at the surface. Okay, so you have dtu, you evaluate it at z equal to zeta. You have u grad u, you do the same, etc. And then when you do this, you obtain a set of two equations which have the structure that actually where you can see what happens. So the first equation is a kinematic equation that I have written in the previous flow. So this is the normal component of the velocity, non-normalized normal component of the velocity. So dt zeta plus v at the surface grad zeta minus the vertical velocity at the surface equal to 0. And then this second equation is when you take the horizontal component of this equation evaluated at the surface. You see that this dtv evaluated here gives you dtv bar plus other terms that vanish with this quantity. So essentially you obtain a set of two equations, one on surface elevation and one on the horizontal velocity at the surface. You see that you have two convective terms and all the complicated stuff happens here. So how do you describe the vertical velocity in terms of the surface elevation and the horizontal velocity? And how do you express, so this is the surface tension coefficient. This is the mean curvature of the water. And how do you express this coefficient A, which is called the Rayleigh-Taylor coefficient? And you see that it pops out just by this chain rule here. It's the dZp evaluated at the surface. So this is the Rayleigh-Taylor coefficient, which you can express using the vertical component of Euler equation at the acceleration of the vertical velocity. Okay, so this is an exact set of the equation. I didn't make any assumption, so you can see the dynamics of the waves fully in this set of two equations. So in order to see how they work, I will just show you, take the one-dimensional case, take a flat surface just to understand first how you can describe this vertical velocity in terms of the horizontal velocity. When you have a flat bottom, the fluid is incompressible and irrotational, so you have a velocity potential which satisfies the Poisson equation in the free domain, which is Laplace of phi is equal to 0. And then you can take the Fourier transform in horizontal coordinate. So the velocity potential satisfies an ODE, second order ODE, which is dz square of phi hat plus minus k square of phi hat is equal to 0. You can integrate explicitly this ODE, so it gives you the velocity potential, which is cosinus hyperbolic of hk, of z. And then once you have this, you can compute the vertical velocity, and you see that you can obtain a very simple relation between the vertical velocity and the horizontal velocity, which reads better in Fourier. These notations mean that if you take the Fourier in horizontal variable, the vertical velocity is given by minus I, the hyperbolic tangent of k, times the horizontal velocity. Okay, so you can pass from the horizontal velocity to the vertical velocity very simply using this operator in the Fourier space. So this is to express this term. Now what is this operator A? So this means when you write these equations, essentially it will behave like this. So you have this convective term, so V dx here in the diagonal term, so they are quite easy to understand. This is when zeta equal to 0, when the surface is not flat, this operator behaves more or less in the same way, so I just put some quotation marks here, but it's behave a bit like this. And then you have this term here, which have essentially this curvature term is a dx square, and you have this Rayleigh-Taylor coefficient. So you have to solve this set of equations, and if you look at the linear version of this equation, in the linear version, this Rayleigh-Taylor coefficient is just g, the gravity, and if you want stability of this set of equations, then it means that the exponential of this, you take Fourier, so you replace d by k, so the exponential of this matrix should be bounded. And this happens only if this parameter g is positive, which means that you have stability when you put the ocean below the atmosphere and not the reverse. Okay, so g has to be positive. And so this is of course the linear analysis. If you want to understand the nonlinear analysis, then the nonlinear stability condition, instead of having g positive, is just obtained by assuming that A, this Rayleigh-Taylor coefficient, is positive. So A, I remind you, is minus the vertical derivative of the pressure at the surface, which has to be positive. That you don't have Rayleigh-Taylor instabilities, which means that you don't accelerate the fluid stronger than gravity. Okay? And in this case, you have stable, you have solutions. Okay, so for one fluid, the conclusion is that you have stability of nonlinear stability of the waves, provided that the Rayleigh-Taylor coefficient is positive. So, okay, so the pressure increases when you go down into the fluid. Okay, so now if you want to understand the importance of this surface tension coefficient for surface waves, just maybe a easy thing is to look at what happens in shallow water, which shallow water is quite important for many applications in oceanography, for instance in coastal oceanography or for tsunami, where you have a horizontal scale L, which is much larger than the typical depth, which is h, and you also have another parameter, which is the amplitude of the wave A. So you have three different parameters from which you can create two-dimensionless parameters that I will call mu. So mu will be the shallowness of the fluid, so it's the ratio of the depth over the horizontal scale to the square. So we are in shallow water if mu is small. And another parameter, which is epsilon, which is the ratio of the amplitude of the wave over the depth. So this is never too big. It cannot be big because the waves break before the amplitude is larger than the depth, but it can be small, okay, or further. Then there is a third coefficient because we have surface tension, which is the ratio of gravity forces over capillary forces, which which is called the bond number. Okay, so ratio of rho g h square over the capillary coefficient sigma. So now, if we want to compare these parameters to see what happens, so what happens if we write the equation in dimensionless form? Well, this operator that I had before, which was minus I tangent hyperbolic of hd, now becomes tangent hyperbolic of square root of mu d, and you can make a Taylor expansion of this one with respect to mu when you are in shallow water. And so this hyperbolic tangent becomes 1 plus mu over 3 dx squared. This is just the expansion of the hyperbolic tangent that I had before. Otherwise, you have the same term here and here. So you have a linear term, and essentially what you can do, you can diagonalize it. So in one dimension, so you have essentially two components of the waves, one that goes to the right, one that goes to the left. Essentially, you can separate these two components, and you can quite easily see that what drives the evolution of the components that goes to the right, if you assume that epsilon is also small, of the order of mu, is described by this KdV equation. So it's transport at first order, at speed 1 in dimensionless variables. Then you have dispersive terms of size mu, and you have nonlinear terms of size epsilon. And then if we look at here the influence of the bond number, you see that you have to compare it to 1/6 here. And if you look at, for instance, typical values for coastal waves, where you have an amplitude of 1 meter, a depth of, say, 10 meters, wavelengths of 100 meters, then you see that the nonlinearity parameter is this, 0.1, mu, the shallowness is 0.01, and this bond number is 10 to the 7. Okay, so you have this parameter, which is really much smaller than everything else in the equation, and so capillary effects are completely irrelevant to describe the propagation of waves at this scale. Of course, they would be relevant if you look at much smaller scales, but at this scale, they do not play any significant role. Okay, so the reason why I mentioned this capillary effect is because when you want to look at now internal waves, so waves inside the ocean, they will play an important role, especially if you want to describe these internal waves using a simple formalism, which is by using the two-fluid formalism, where you have a sharp stratification in the density of the water in the ocean. And so what you do, you assume that you make the rigid lead assumption, so you neglect the surface waves, so you assume that you have a rigid lead at the surface, and you have two fluids of different density, rho minus and rho plus. Rho minus is smaller than rho plus. And then at the interface between these two fluids, you have propagation of waves. Okay, so this is the simple formalism that you can use when you want to describe waves with a very sharp stratification that you model like this. So what is the difference when you do this? So in principle, it's a bit the same because you just have one interface to describe, like in the water waves. Instead of having air with rho minus equal to 0, you have another fluid with rho minus, which is non-zero, okay? Which is smaller than rho plus, but non-zero. So when we had one fluid, I said that at least in the linearized case, the stability was governed by this matrix, which for each mode k is this, k tangent hyperbolic of hk, and this one. And in the case of the nonlinear equation, so this was stable if g was positive, and in the case of the nonlinear equation, this is replaced by positivity of the Rayleigh-Taylor coefficient. Now for two fluids, what happens is that if you look at the linearized equation like this, you don't see much difference. You have exactly the same matrix. The only thing that happens is that you replace gravity by relative gravity. So as long as rho plus is larger than rho minus, then you still have stability. This is still positive, if g is positive. Okay? So you just have to put the heavier fluid below the lighter one. But then, if you look at the stability of the nonlinear equation, there is something new here. And the something new is that you can have a discontinuity between the tangential velocity of the two fluids. And if you look at the matrix, the component, the influence of this shear velocity, so this is the jump here of the horizontal velocity at the interface, then you have something which behaves like modulus of k for the kth mode. And you see that this has the bad sign. As I said, the stability, for stability we had to have this quantity positive, this quantity positive, this quantity positive. And here we need something positive, but you see that this is positive, and this is negative. So since this is a constant, you see that for high k, if you don't have surface tension, this will be negative, and you are sure that you will be unstable. So the nonlinearity creates shear velocity, even if you don't have it initially, and this creates instability of this, and you cannot have stability of wave, you cannot have well posenness. This is why surface tension is important, because if you add surface tension, then you put something which behaves as k square, and essentially you can have stability for all modes, provided that you can stabilize the low frequencies when k is small by the positivity of the Rayleigh-Taylor of this Rayleigh-Taylor term, and if you can compensate this term for large k by the surface tension. Okay, if you don't, you have a parabola, and this parabola must not go into negative values. Okay, so this is a very new phenomenon specific to two fluids interfaces. So this is the same matrix that I wrote. And so when, so in general, if you don't put surface tension, what happens is that you have these instabilities, which are of course the Kelvin-Helmholtz instabilities when you have shear velocity. But yet we observe these waves at the interface between two fluids, so there are some possibility to observe them, and there are two stabilizing factors, and this is what I explained with this parabola that must not go into the negative value. So it means that this quantity must not be too negative. So what does it mean? It can be the case in two configurations. So the first one is if rho minus is much smaller than rho plus. Actually, these are the relative density, I'm sorry. So if this is the case, for instance, this is the case for the air-water interface, if you look at surface waves and decide to take into account the density of the air, then in this case, the density of, relative density of the air is much smaller. So you see that this coefficient here is small, and that you will be able to absorb this quantity by the gravity for the low frequencies up to a very high frequency until which it will be absorbed by this one. Okay, so this is the first stabilizing factor. And the second stabilizing factor that you can observe in experiment when you have two fluid experiments, so you can propagate. So these are a solitary wave that you send at the interface of two fluids. So you can propagate solitary waves of larger and larger amplitude, but at some point the wave is too strong, creates too much shear velocity, and it is destroyed by Kelvin-Helmholtz instabilities. So this stabilizing factor is really for internal waves, where you have two fluids of different density, but the two densities are close enough. So you cannot explain the stability of this wave by this argument that rho minus is smaller than rho plus. And the other possibility is just that the jump of the shear velocity is very small. This is the only way, other stabilizing factor that can happen. So you have to look at the size of this shear velocity, the jump of shear velocity. And you can do it, for instance, by looking at what happens when you are in the shallow water scaling, where you can assess the size of the different quantities that you have. And so in the end, you can say this, so that in the one fluid case, the stability was governed by the Rayleigh-Taylor coefficient, which was this, minus dZp positive, which in the linear case degenerates into this, that the gravity is positive. And when you have two fluids, you have a generalization of this Rayleigh-Taylor condition, which is that the jump of the vertical derivative of the pressure must be smaller than some coefficient that depends on the densities times the jump of the horizontal velocity to the power 4. And then you have stability of the waves. In this case, if this is satisfied on a time scale that depends only on this parameter. And if you look at what happens in the shallow water scaling, where you are able to assess the size of the pressure, the size of the velocity, etc., you can have a dimensionless number, which says that when this dimensionless number is small, then you can have propagation of a stable wave at the interface of two fluids. And you see, for instance, the influence of the amplitude, that if you have an amplitude which is too large, as in the graph that I showed you here, then this criterion might not be satisfied and you have Kelvin-Helmholtz instabilities. But you see that surface tension is absolutely necessary. When surface tension is 0, then this is infinite and this will not be true. Okay, so for the propagation of two fluid interfaces, you need surface tension, otherwise you don't have propagation of anything. It's destroyed by Kelvin-Helmholtz instabilities. So of course this is a bit problematic in the sense that if you look at the ocean, you don't have really surface tension. You have water of different densities, so it's not two fluids, it's, and you don't have a sharp interface with surface tension between both of them. This could happen between other fluids, but in the ocean this is not satisfactory. So of course you could use this formalism and add some surface tension coefficient and match it with your experimental data in order to modelize what happens by a two-fluid model with surface tension, but this is not really what happens. What happens really, and this is what I'm going to do now, is that you have a continuous stratification of the density of the water, and that you must be able to understand what happens. So this is a joint work with Benoît Desjardins and Jean-Claude Saut. And so what is the formalism in this case? So I'm still in the rigid lid approximation. So I have rigid roof and rigid bottom. And now, so I'm in a strip, minus h to 0. And the equations are still Euler's equation. So rho dtu plus q grad u, and the pressure term and the gravity term. Now, the difference is that rho is not constant anymore. The density is not constant anymore. So you have the equation for rho, which is dt rho plus q grad rho is equal to 0. And you have incompressibility, which is here divergence of u is equal to 0. Okay? Of course, I do not assume anymore that I'm irrotational here. So these are the set of equations. And I need some boundary condition, which is just that the two boundaries are impermeable. So the velocity has to be tangential at the bottom, which is located at minus h, and at the surface, which is located at 0. Okay, so these are the equations. So what are waves for this? What could correspond to propagation of waves in the ocean with this? So the first thing that we can say is that they will appear if we look at perturbation of equilibrium solution. So you have an equilibrium solution, stationary one. I will take the case where you don't have horizontal velocity. So you have an equilibrium solution for the velocity, which is u equal to 0. So you have 0, 0, 0 here. And in this case, you must have 0 on the right-hand side, which tells you that the pressure must satisfy this, is given by an equilibrium density ρ, which is a function of z only, and dzp must be equal to minus ρg, which is the hydrostatic pressure. Okay? And of course, this you can check that this is satisfied everywhere. So this is 0, dt rho is 0, and the divergence of u is 0, of course. Okay, so this is the equilibrium solution. And then you look at perturbation of this equilibrium solution, for instance, a perturbation provided by the tide, for instance. Then you look at exact solution, which are perturbation of this exact stationary solution. So you take this perturbation to be of the form epsilon u, so perturbation of this. The perturbation of this, which will be, so this equilibrium stratification plus epsilon rho, and a perturbation of the pressure, which will be this hydrostatic pressure plus epsilon p. And now you want to write down the equation for u, for rho, and for p. So you look at, you plug this into the equations, and you obtain equation that, of course, have a structure which is a bit similar to the original one. So you have the equation for u, which is dtu plus epsilon u grad u. You have the pressure term, so it's minus 1 over, so the total density, which is the equilibrium density plus epsilon rho. And you have the other one due to the gravity. So the new thing is maybe here for the density equation, which is dt rho plus epsilon u grad rho plus rho prime of w is equal to 0. Rho prime is the vertical derivative of the equilibrium density. You see that when you write originally you have the total density, the equation was dt rho plus epsilon u grad rho is equal to 0. When you plug rho ec plus epsilon rho in this equation, you see that you have the term w times dz of rho ec, which is this one. Okay? So you have this new term, which with this component coefficient depending on z, and which complicates the analysis. And you will still have incompressibility of the perturbation with the same boundary condition. So you can prove that you have solution for this equation. The problem is not to know that you have solutions. The problem is to be able to describe this solution and understand what is a wave, what will be the speed of the waves here, what will be. This was quite obvious in the case of one fluid or two fluids with sharp interfaces. Now it's maybe less obvious. So how do this solution look like? Finite time, yes, excuse me. Yeah, finite time. Yeah, I'm sorry, you're right. And so what I will do is just look at first the linearized equation, meaning that I take epsilon equal to 0. I just look at the linear variation of these perturbations. So the equations are this. So much simpler, of course. So you have rho equilibrium dTv plus grad p is equal to 0, dTv plus 1 over rho equilibrium dzp plus rho over rho equilibrium g equal to 0. This is for density, dt rho plus rho prime of w is equal to 0, and the incompressibility condition, and of course the boundary condition. Then, so this is the question that many of you, I guess, know. You have simple computation that can lead to this equation. So you want an equation, so for you can replace rho, excuse me, the pressure here, you can replace the pressure here by a function of rho and w using this equation. And then you can replace the equation of w by this using this equation. And in the end, you obtain an equation on w of the vertical velocity, which is given by this. So this is a complicated equation. It is square of Laplace plus 1 horizontal Laplace plus 1 over rho equilibrium dz, rho ec dz applied to w, plus n square horizontal Laplace of w is equal to 0. And this quantity n square is called the Brunt-Weisseler frequency. It's given by minus g, rho equilibrium prime over rho equilibrium. So this is positive under the assumption that the density increases when you go down into the fluid. So you have a stable stratification, which means that rho prime ec is negative. Okay, so this is a positive quantity. So if you want to solve this equation, so it's a bit complicated because this coefficient in general depends on z, on the vertical variable. This depends on z, this depends on z. And here you also have variable coefficients. So a good way to transform this into a simpler equation is to remark that here you have a kind of Sturm-Liouville operator. And so if you want to diagonalize this operator, it's convenient to introduce a decomposition of the vertical velocity on a Sturm-Liouville basis, which is the following one. You assume that the vertical velocity, which is a function of t, x, and z, can be expanded as a sum of an infinity of mode. So the modes are the function fn, which are a function of z. So this is the vertical stratification. And the coefficient are function of t and x. So for each mode, you have a coefficient which is a function of t and the horizontal variable. And what are these vertical modes? Well, they are the orthonormal basis of L2 of the interval minus 1, 0. So I have, actually, it should be minus h, the vertical depth. So with this weight and associated to this Sturm-Liouville problem. So you have, for this Sturm-Liouville problem, you can find the basis like for when rho equilibrium is constant, for instance, you have, you can diagonalize the operator dz square by using sinus and cosinus. So this is a generalization of this when you have variable coefficients. So you have a basis of L2, like the sinus and the cosinus are a basis of periodic functions, with eigenvalues that I have written under this form, 1 over Cn squared. So Cn will be a speed. And so each function Fn diagonalize this second order operator because it's equal to this function fn with a coefficient which is 1 over Cn squared, and this is the weight of your scalar product. And with a two boundary condition that it should vanish at the bottom and at the top. And the eigenvalues are 1 over Cn squared, and so they go to infinity when n goes to infinity, which means that Cn goes to 0. Okay, the speed goes to 0 when for higher mode. And you can do the same kind of decomposition for the horizontal velocity, for the pressure, and for the density. And then you plug this, so you have this expansion here, P, rho, etc. And now you will plug this into this equation and look at what happens on the coefficient and find equations for the coefficients. So if you look at what happens, for instance, for this equation, so I take this equation, I will take the scalar product with the function rhoec fn. So you see that rho is a function which is rho over rhoec. So when I multiply this rhoec simplifies, so it will be just rho times fn. And so I will have fn minus rho prime times fn. So this is an orthonormal basis for this scalar product. So this will give you 1 if you have n here. Okay, so this gives you the rho n, the coefficient here. The same for Pn, but here you see that it's a bit different for the vertical velocity because the vertical velocity, it's dTvn on the basis which is Fn. So you have Fg rhoec Fn, and this in general is not an orthonormal basis for this scalar product. This is, the Fg is orthonormal for the scalar product with the density which is this one, which is minus rho prime equivalent, or equivalently this is this one. So you see that it's orthonormal if n square is constant. If the Brun-Weisseler does not depend on z, because in this case you can take it out of the picture. So just assume that n is constant, which means that you have a exponential stratification in the ocean. So in this case, you can take the n out of this, and this is an orthonormal basis, and you find that this is equal to n minus 2, and this is equal to 1 if g is equal to n, or to 0 otherwise. And in this case, you obtain a set of equations on Vn, ρn, etc. And what you obtain is a very nice set of equations here on Vn and ρn that you recognize something that looks familiar when you look at waves. So if you don't have the red term, this is a speed equation, wave equation at speed Cn. For the nth mode travels at a speed which is Cn, which is correspond to the eigenvalue of the Sturm-Liouville decomposition. But in addition to this, you have a dispersive term here. And this is a bit surprising for those who maybe know water waves or two-fluid models, where in this regime where I am not in shallow water here, normally you have dispersion relation, dispersive term that appear through a very complicated object, like the hyperbolic tangent that I had before, which is linked to a Dirac-Neumann operator. Here it appears with a simple differential operator. Okay, normally these operators, they appear, but as I showed you when I derived the KdV equation, they appeared through a shallow water expansion of a non-local operator. Here they appear like this. The non-locality, of course, is in the decomposition and the vertical modes. So you have this interesting decomposition, I repeat, when n is constant. So what does it mean to have n constant? So I just plot you here an example of a continuous stratification. So it looks constant, but it's exponentially stratified with a small stratification. So here are the eigenvalue, the speed that correspond to this stratification. You have several speeds like this. And these are the corresponding eigenfunction for the Sturm-Liouville decomposition. So you will decompose your stratification into functions like this. And of course, these, for constant stratification, these functions are sinus and cosinuses. So you are just doing a Fourier decomposition of your vertical stratification, and then find equation for the coefficient on this Fourier decomposition, like when you do Fourier expansion on to solve the heat equation, for instance. But of course, n in some cases is not constant. For instance, here I have taken the case of a continuous stratification, but I have included two sharp stratifications. So here and here you have a jump in the stratification, and so in red is the derivative minus the derivative of the stratification. So you see that you are converging to two Dirac functions. So these are the speeds, and you see that here the eigenfunctions are a bit more complicated. And okay, so it's a bit more complicated, and you cannot really approximate this by sinus and cosinus. And so you need to understand what happens when n is not constant. So as I said, when n is not constant, this term that you had, this is the Fg is not an orthonormal basis for this scalar product. So actually, instead of having this simple set of uncoupled dispersive wave type equations, then this term will couple all the modes, and what you obtain is that you have, when you look at this term, you can call them alpha jn. There are some interaction terms, and what you obtain is a sum of coupled equation of this form. Okay, so you have interaction between the different modes and transfer of function. Even though you don't have nonlinearities, you have this transfer between the different modes. Okay, and so maybe just one last word. What happens if you want to understand the effect of nonlinearity? So in this case, I will look at n constant because it's already complicated enough. And I will look at the shallow water regime where I work in dimensionless variable. The influence will be to have this small coefficient mu in front here. Okay, so essentially, at leading order, you have a hydrostatic pressure for P. And what happens, I will just, because time is short, I will just comment on what happens. So in the linear analysis, I showed you that you have a set of uncoupled dispersive type wave equation in blue here and red. And when you put the nonlinearity, then you will have the nonlinear terms, and you have to take the scalar product of this nonlinear term with the nth mode Fn. But of course, this will reintroduce a coupling of the different modes, because when you look at this nonlinear term, for instance, just the convective term, which is like this, it's a sum of the coefficient of u, rho, etc. So it's these terms. And what are the alpha n pq? They are due to the fact that you will integrate a product of the eigenfunction associated to the u and rho with Fn. So you have these interaction coefficients. And in general, there is no reason why they should be uncoupled. Okay, so you have a set, because of the nonlinear term, to couple all the modes. But the good thing is that you still can decouple the equations by just remarking that the contribution of the coupling term, I'm sorry for that, the contribution of the coupling term can be discarded in the sense that when the waves, what happens is that the different modes essentially travel at different speeds, so they separate one from each other. And so the coupling term, so this is another argument of to decouple them, is an asymptotic argument. Since the different modes travel at different speed, the coupling term, when they are for times large enough, they don't see each other. They're too far one from each other to interact, and so they have a contribution which is small. So what happens is that at the beginning you have all the modes that are coupled, but then after some time they are far from one from each other, and so you obtain a set of uncoupled Boussinesque type equation. And I finished it. I'm sorry for the hurry.
Maybe you have time for one short question?
Well, it's more of a comment. Yeah. Thank you very much for a beautiful presentation of the topic. I just wanted to comment on the fact that you might be interested in the atmospheric case in which there's no rigid lid. The atmosphere, the equations are on an infinite interval because the density decreases exponentially. But it has been shown by two students of mine from the Courant Institute, Steve Cohn and Dick D, that you are in the limit point case of Titchmarsh-Kodaira theory. And so you still have a finite, finite series. The point has been raised by Dick Lindzen, who, aside from being the only halfway competent climate change denier, is a denier of pretty much everything. And so the point was the general circulation models of the atmosphere are thoroughly wrong because you do not have a finite spectral decomposition of you cannot discretize in the vertical. So Cone and D or D and Cone showed that that just ain't so. So
Okay.
you might be interested in
thank you.
looking at this.
One question, and then for other people, so I think that David will be here all week, so if you have questions to ask.
I just wonder whether your approximation in the nonlinear case, does it conserve appropriate energy?
Yes, you have approximation. So in the uncoupled case, you have conservation of the energy up to terms of epsilon square. It's approximate conservation of energy, which is the same when you look at this kind of approximation for water waves. You have only approximate conservation of energy, which correspond to the accuracy of the model, actually. But you do, yes.
Okay, well, let's thank David again.